Right. Today we're talking about digital logic gates. Okay. Um, we start with, I suppose, what is digital, right? What does the word digital mean? We're all kind of living in this digital world where we have computers and smartphones, and we're all used to the internet, Snapchat, and whatever. But what does it really mean? Okay. So in the digital, all inputs and outputs are signals, right? And they're always either on or off. There's no in between values. There's nothing like that. There's no point fives and point sixes. It's either on or off. I want you to think about it like a light switch, right? When you come in and you flick on the light switch, it's either on or it's off. Okay? And on would represent a one, or would represent an on, or zero would represent not on or off. Um, so I suppose where are we using these things, right? Digital systems are made up of many logic gates, right? The fellas that you can see in front of you there. The main chip in your computer or in your phone, it could have millions of them, okay? And they're all working at the same time in order to give you whatever you're looking at. Um, Logic gates, they're called gates, I suppose, because they act like a gate to control whether an input signal is allowed to get to the output. So, uh, if you look at the diagrams there, you have an A or a B on one side, and then a decision, I suppose, is made inside the gate whether to allow a signal to get through or not to get through. Okay? A logic gate has one or two inputs and one output. Okay? Because a logic gate is a digital device, its inputs and outputs are always ones or zeros. The operation of a logic gate is fully described using a truth table. You can see there on the right hand side the truth table for each gate. Okay? A truth table tells you what the value of the outputs will be for every possible combination of input values. Okay? So those are the possible outcomes. The symbols and truth tables for each logic gate are shown over on the page there. A and B are inputs, and the Y columns in all the truth table are all the outputs. So we're going to start off with a NOT gate, right? So this is a NOT gate, and the output is always the opposite of the input on a NOT gate. Okay, so it's an easy one to remember. When you have 1 as an input on A here, the output is always 0. If you have 0 on the input, it flips it around, and the output is always 1. So that's that's the most basic logic gate. It's called a NOT gate, and that is the symbol there. Next one is an AND gate. I suppose this one is kind of an easy one to remember because it needs both of them. It needs to be working together. So they're AND. Two of them working together. So A and B need to be 1 in order for the output to be 1. So if we go over to our truth table here, if A is 0 and B is 0, then Y is 0. If A is 0 and B is 1, well, the two of them aren't the same, then the output is 0. If A is 1 and B is 0, then the same situation as above, Y is 0. But the only situation where we get a 1 is when we have both A and B are 1 and 1 together. Then we get a 1. So that's an AND gate. OR gate, I suppose if you were looking at the truth table, then you would say the opposite is true for an OR gate. So if either one of these is 1, then the output is going to be 1. Look over the truth table here. If A is 0 and B is 1, then we get a 1. If A is 0 and B is 0, we get a 0. If both A and B are both 1, then we get a 1. And then if A is 1 and B is 0, you get a 1. Okay, so if either one of the inputs is 1, we get an output of 1. Okay, now we move. These are the most basic 3. These first 3 are basic ones. The NAND gate and the NOR gate, then, however, they're kind of combinations. Okay, so a NAND gate is a combination, as the name might say or suggest, of an AND gate. So we have AND gate, which is this fella here. I've drawn it down here, followed by a NOT gate. So the N for NOT. So AND first, and then NOT. So how does this work? Well, you could just learn off the truth table, or you could figure it out for yourself. So if A and B are both 1, an AND gate, as we know, if the two of the inputs are 1, then we'll have a 1 here. But then this 1 goes through the NOT gate, is switched around, and gives us a 0. So when we have both of them as a 1, we have a 0 over here. We can go over to our truth table. When A and B are both 1, we have a 0 over here. When we have A and B different, so either A is a 1 and B is a 0, or B is a 1 and A is a 0, an AND gate will give us a 0 here as the output. But since it's also going through the NOT gate, that flips it around and gives us a 1. So if we look up here where the two of them are different, a 0 in A and a 1 in B, we have a 1 as the output. We have a 1 in A, a 0 in B, we have a 1 as the output. And then lastly, where both of the inputs into that are 0, we have a 0 and a 0, that will always in an AND gate give us a 0 output. But then since we're going again through the NOT gate, that will flip it around and make it a 1. Okay, so this, if you can't learn off the truth table, or if you just can't remember that an AND gate will, it will flip it around depending on what the inputs are. If you can't remember that, if you can't remember the truth table, it's good to just draw out what the two other logic gates are. So draw out the AND gate and the NOT gate, and it'll be fairly simple to work it out afterwards. Now, the opposite then can be said for the NOR gate, right? The NOR gate is an OR gate, which is this guy here. We've looked it up there, followed again by a NOT gate. So an OR gate followed by a NOT gate. Okay, so the same thing, we go through the same thing. In our OR gate, we found above there a second ago that if either one of these is 1, so say if that is 1 there and that's 0, then this one has to be 1. And if that is 1, the NOT gate flips it around and gives us a 0. So more often than not, what we have here are zeros as our outputs, and we'll have one case where we have a 1. The only case where we'll have a 1 as an output for an OR gate is when both inputs are zeros. So the 0 here and the 0 there will give us a 0 here, because neither of them are zeros on the inputs, and then it'll flip it around and make it a 1. Okay, so those are basic logic gates. Okay, these ones here, right, this one here can be used to make up almost any logic gate combination. Okay, so that is one of the most common ones that are used in computer chips, the NAND gate, and I suppose in modern technology, it is one of the most important pieces of digital technology that you have in all of your devices and things like that. Okay, that's just a basic start into logic gates, and we'll do a little bit more on that again. Okay.